So after all this theory, let's now look at some examples of affine schemes. And the first one is one that we have already seen a bit, that we can now do properly, namely the double points. So let's take for R this ring, which is k of x modulo x squared, where k is a field. Then we see that x we can see as an element of R, and R, as we have seen, is just the set of all global functions on spec R. And the interesting thing is that this x is now a nilpotent element, right? Because if you take it to the power 2, you get 0 as a function. And this is already something which we know is not possible for the affine varieties over a field, because there the coordinate ring is always supposed to be reduced. And this leads to some interesting behavior. So to see this in general, let's see what is spec R. Let's derive it from first principles. So we know that any element in this quotient here can be written, in fact, has a unique representative of the form phi equals to a plus bx, where a and b are elements of k. And so the first thing we want to do is look at what are all nilpotent elements. And this is not so hard to do. So if you raise this to the power n, then you apply this binomial formula. And you see it starts with a to the n. The next term is n choose 1. So just n times a to the n minus 1 times bx. And then all the other terms would be higher powers, would have higher powers of x. And these higher powers are all 0. So in fact, it already stops at this point. This is the full phi to the n. And then what does it mean for this to be nilpotent? So then this here has to be 0, but we see it's the unique representative as before. So this means this has to be 0 and this term has to be 0. But if a to the n, where a is now an element of the field, if this is 0, then the field has no non-trivial nilpotent elements. So then this means a must be 0. But on the other hand, if a is 0, this is already enough because the second term then also vanishes. So somehow this thing is nilpotent if and only if a is 0. But if a is 0, then you see just a multiple of x. So in other words, this is equivalent to saying phi is in this ideal generated by x. So we see the nil radical, the set of all nilpotent elements, is just this ideal generated by x. And this is already helpful because we know any prime ideal must contain all the nilpotent elements. That's some very basic property of prime ideals. And on the other hand, so this thing, this ideal, we claim is also a maximal ideal. And that's easy to check because if we just take the quotient of R modulo this, then not just x squared is 0, but actually x itself is already 0. And then we have nothing left of this polynomial ring. We just get k back, but k was a field. And so the quotient being a field is equivalent to this being maximal. So we have seen any prime ideal must contain x. And on the other hand, x is also a maximal ideal. And this shows it's actually the only prime ideal. So this is a single point set, and that's what we had already claimed before. And the interesting thing is the field associated to this point. Well, this then you take exactly this quotient. So the field is the field k that we started with. But so this means if we now interpret this phi here as a function on spec R, then its value at this point, so this value lives inside this field, and well, you just map this element here to this quotient, and this just means you kill this b times x part, and so this value is just a. But this gives an interesting example because this means phi is a function on all of spec R, but its values at all the points, namely at exactly the one point that we have, do not determine phi completely, because we cannot reconstruct what the b is from this value. So this is so this spec R shows us a lot of things that were true for the affine varieties are no longer true for the schemes. For example, the functions are not determined by their values at all the points here. Okay, so this is something that one has to kind of give up when one goes from schemes to varieties. You need to specify these functions in some other way. Okay. And so this was a bit of algebra, and then the geometric picture that you can have in mind is that the spec R, you can, as we are going to see a bit later, the spec R sits inside the affine line like this, so in spec K of X, and you can see it as a point sitting at 0, but in fact it's what is called a double point, or sometimes a fat point. So it's not just a single point, but it has a bit of like infinitesimal direction in this x direction. In particular, what this means is that if you have a function f and k of x, this would be a global function on spec k of x, and you restrict it to this point. What this means is you take it in this quotient k of x modulo x squared, and then what you see here is it exactly remembers not just the value at the point 0, but it also remembers the kind of first order behavior of the function at the point 0. So for example, from this restriction, you can still recover what the derivative of the function at the point 0 is. But on the other hand, it only remembers this linear part, so you cannot reconstruct what the second derivative at this point is. Okay, and this thing will be very useful if you continue studying this scheme theory. Okay, this was one example which has nilpotent elements, and then another, a very basic ring that all of us know for a long time is just the integers. And so the spectrum of the integers, so somehow the set of prime ideals we have already seen is kind of, we have 0 and then 1 for each prime number. And so somehow spec R you can write like this, yeah, just a sequence, 1 point for 0 and then 1 for each prime number. Then we can also write down what is k of p, namely the fraction field of the quotient. And so here z modulo 0 is z, and then if you take the fraction field, you get q. And then at all these other points, you get these z modulo pz's. And now what we have seen is inside there we have some distinguished open sets. So for example, distinguished open set associated to the element 6 in Z. Let's see what this is. So this D of 6 is spec R modulo the vanishing set of 6. So it's the spectrum minus the set of prime ideals such that this ideal generated by 6 is contained in the prime ideals. In other words, 6 should be in the prime ideal. So, well, this excludes the 0 ideal. And, well, 6 is in one of these ideals generated by a prime number, if and only if the prime number divides 6. So in other words, if and only if we are prime number 2 or 3. And so D of 6 exactly removes these 2 points here. And so the open set looks like this. And then we can also write down a function now on this open set. And the function that we can take is, for example, 5 divided by 6. That's a perfectly good function because we divide by some power of 6. And then we can see what does it mean to evaluate this function at various points. Well, it basically just means making sense of this in this field associated to this point. And so, for example, at 0, we need to get a number in Q, and the number that we get is just 5/6. So we get back this entire fraction. Whereas at these other points here, we need to get an element of this finite field. And what we there do is, well, by ensuring that P does not divide 6, 6 is an invertible element in Z modulo PZ, and so it has an inverse. And then we can just get the element 5 bar times 6 bar inverse. And just to give an example, So at this point, z modulo 5z, this function actually has a 0, right? Because 5 bar is equal to 0. So this is this function, the vanishing locus of this function is actually exactly this single point here. And then at other points, so for example, at z modulo 11, there you can check the inverse of 6 modulo 11 is 2, because 2 times 6 is 12, and 12 is equal to 1 modulo 11. So this works out. And so 5 bar times 6 bar inverse is exactly 5 times 2 is equal to 10. So it's 10 bar. So you can just evaluate this function at this point. Okay, so these were just some concrete examples to get a bit of a feeling for these distinguished open sets and for the functions on those.